everyone. So CCIP, I believe, was announced 1 year ago at SmartCon. And so I'm very excited that today I can share an update on where we are with it and concrete technical details on its architecture. So why is there even a need for something like CCIP? Why do we care about interoperability? Well, we live in a multi-chain world, right? Chainlink is live on 15 chains today. Some of these are L1s, like Avalanche and Ethereum. Some of them are L2s, like Arbitrum and Optimism. And then we have EVM chains, again, like Ethereum, and non-EVM chains like Solana. So it's a very heterogeneous set of chains we're targeting. And we want them all to be able to talk to each other and interoperate. And in fact, we're seeing that major dApps are moving towards a future where they're natively cross-chain. So for example, Aave with their portals and Synthetics with their synth teleporters, both are integrating natively cross-chain features into their dApps and allowing users to seamlessly move liquidity between chains. Oh, perfect. This is also borne out by the numbers. If you look at how much value has been bridged, then estimates show that $168 billion worth of funds have been bridged, and over 2/3 of that, 68%, or 115 billion, has been over the past 12 months. So demand for this seems to be increasing. And this can be for a number of use cases. So first of all, of course, trading, as always in DeFi, is sort of the most obvious use case. But then also for things like collateral. So if I think about lending protocols with cross-chain interoperability, I can have a lending protocol where a user deposits funds on one chain and then borrows against that collateral on another chain. I can also think about things like cross-chain governance, where I have a cross-chain dApp that has a governance vote happen on one chain, whose results are then propagated to the various other chains it's also running on. And then, maybe more towards the future, we have things like entirely new kinds of dApps, which maybe take advantage of very positive network effects on Ethereum, where a lot of liquidity and a lot of activity happens, but then they also want to harness compute and storage capabilities that other chains offer that are not available on Ethereum. And so with something like CCIP, they can be natively cross-chain and go back and forth between Ethereum and the other chain to get the best of both worlds. And then finally, enterprise workflows, enabling enterprises to more easily interact with the blockchain. But there's a problem. So it's unfortunately not quite as easy as one might think, right? As Sergey said, it's easy to launch a cross-chain bridge. It's hard to do it well and to do it securely. So cross-chain protocols are inherently complex. We're targeting different chains. You need to compose together different systems, different programming languages, different technologies. They also present a large attack surface because any adversary that can access any of these public blockchains can now interact with your protocol. And so if you have a vulnerability anywhere, they can come in and exploit it. And then the adversaries we're now seeing, right, are not just some script kiddie sitting in their parents' basement. We're talking about sophisticated state-level actors targeting these cross-chain protocols. So it's a very challenging environment to operate in. And once again, this is borne out by the data. So $2 billion worth of funds have been stolen in cross-chain bridge hacks to date. There's a nice graphic here showing this in more detail, prepared by Chainalysis. And just this year, just in 2022, there have been 8 attacks, $1.3 billion stolen. And in fact, more than 2/3 of the funds stolen in hacks in 2022 are from cross-chain bridge hacks. So this is now the dominant mode of theft or exploitation in the blockchain ecosystem. And this then directly informs our architecture considerations. So security comes first, right? And when we say security, we mean end-to-end security, so looking at the entirety of the system. That means hardening each component, fuzzing it, auditing it, static analysis, testing, you name it. Any kind of technique that one can apply to make individual components more secure, we want to consider using. It also means, in terms of your architecture, minimizing single points of failure, right? So as great as it is to try to make each component as secure as possible, individual components might still fail. And so it's great if, in terms of my architecture, I can have safeguards in place. And I can minimize relying on single components for the security of my entire system. That also means practicing defense in depth, so that if an adversary manages to breach some first layer, there's another layer that awaits them. And it means for us specifically that in terms of design philosophy, we care more about safety than about liveness. So if there's some kind of scenario where a fault occurs, and I can choose whether that's going to be a safety fault, which would mean that, for example, some message is transmitted across the bridge which was never actually sent on the source chain, or I can choose to kind of turn that into a liveness failure where maybe the bridge pauses. I'm going to choose safety, right? I want the bridge to be safe, and I don't want any messages that weren't actually sent to go across it. If the bridge pauses, not ideal, but in that scenario, preferable. Then another major goal, as the name CCIP, Interoperability Protocol, already implies, is, of course, interoperability. As I had mentioned, we want to connect contracts on heterogeneous chains. And we also want to be forward-looking. The ecosystem is still evolving, and we want to be able to have CCIP evolve alongside the ecosystem. So if new chains, new technologies emerge, we want CCIP to be able to integrate with them. And then finally, of course, as Steve Ballmer once said, developers, developers, developers. So we deeply care about the developer experience of devs that are developing against CCIP. The focus of the product is to enable developers to, as I mentioned, build natively cross-chain dApps. And that means that they should be able to send arbitrary data between the different contracts running on different chains that belong to their dApp. That means that they should be able to send value. That means, for example, tokens between the different contracts running on different chains. Because ultimately, right, DeFi and finance are probably the dominant use case of blockchain today. And we want to be able to abstract away the complexity of securely handling that value for them, rather than having to ask every dev to build their own solution for handling value on top of some kind of messaging. And then finally, we want to offer an easy-to-use API. And I'll show you the API in a bit, and hopefully you'll come away convinced that it is indeed easy to use. Cool, so let me start talking about the architecture, and I'll talk about it at a high level first, and then we'll go into the details more. So roughly speaking, we have the stack here, where at the top we have applications and user interfaces that are developed by third-party developers. And then all the other layers here that have a Chainlink logo on them, those are developed by Chainlink Labs. And so at the top here, we have the CCIP programmable bridge, which is the part that applications directly interact with, which sits on top of a secure transport layer, which is responsible for moving information between the different chains in the system. And then that, in turn, sits on a foundation of OCR2 and the decentralized Oracle networks powered by it. And then maybe unique to kind of CCIP and unique in the cross-chain space, on the side, we have this completely separate system, the anti-fraud network, which is responsible for independently monitoring everything happening in the primary system here on the left, and making sure that if there's any kind of issue detected, that issue can immediately be recovered from, that if any kind of, for example, issue happens during transport, that message that was sort of mistakenly transported cannot even be executed. So even if an adversary were to somehow compromise the layer on the left, the FN on the right would still prevent bad things from happening. And I think this ties back to what I said earlier about minimizing single points of failure and practicing defense in depth for security. All right, so now we get to the fun part, the architecture deep dive. So let me say at this point that this is based on joint work with these awesome folks. We're very fortunate to be working with great academic advisors like Dan Bonet, Ari Jules, Andrew Miller, and we're also very fortunate to have a very dedicated core team of researchers and engineers working on it. So I want to give a shout out particularly to Kostis, Alex, Renz, and Connor. So without the contributions of all these folks here, this wouldn't be happening. OK, and now, in order to be able to talk about the architecture, let's start out by defining some terminology. So CCIP enables a sender on a source chain to send a message to a receiver on a destination chain. Sender and receiver are both smart contracts. The source chain is the contract the sender runs on. The destination chain is the contract the receiver runs on. And then we have the message, which consists of data and tokens. Now, you may have noticed, right, I talk about one source chain and one destination chain. And there are some arrows missing here. Anyways, the point that I want to make is that we have one instance of the protocol that we're talking about, but you should imagine that there's many protocol instances running in parallel, connecting the different chains with one another. So this is actually a kind of fully connected graph, but we're always going to be talking about a single instance of the protocol here. And then there's a router contract, as you'll see in a second, that makes sure that a developer doesn't have to worry about the details of what protocol instance is responsible for getting a message transported between different chains. So yeah, going back to this architecture overview, you see that this is color-coded, and I'm now going to show you the components of the system and explain to you what parts of the stack they sit in. So here we see the major components of the system. There's 3 domains, right? We have a source chain, an off chain, and a destination chain. All the things with a squiggly line on them at the bottom are smart contracts. And then the committing DON, the FN, and the executing DON, those are all distributed systems consisting of multiple replicas, multiple oracles. So there's just a box there, but you should imagine that there's many nodes running this. So in white, we have the sender and receiver contracts written by external developers. Then in light blue, we have the components that form the programmable bridge. Can we go back one slide? No? OK, whatever. And then in kind of just blue, we have the transport layer. And then in this kind of blackish color, we have the AFN. And so again, the programmable bridge sits atop the transport layer, a CCIP core, which in turn sits atop the DONs powered by OCR2. And then on the side, we have the AFN that makes sure that everything is working correctly. Perfect. So this is the API that a developer has to worry about for sending messages. And so while I'm going to explain to you all sorts of complexities in terms of how the architecture functions, what I also want you to take away here is that a developer doesn't have to worry about that. A developer only has to worry about sending messages and receiving messages, and everything else is abstracted away. So here we have a router contract, which is what the sender contract will talk to, and it will just call this solidity function here in this example, CCIP send, where we pass in a destination chain ID, telling the router to what chain we want to go, and a message, which you see here as a structure consisting of a receiver, so that's just the address that the message should go to, some data, and tokens and their amounts, as well as a gas limit for execution on the destination chain. One thing that I want to point out here is, right, the developer has the option to specify data and tokens, but if they want to, they can only specify data and leave the tokens empty, right? So if you only care about messaging, you don't have to use the token functionality. Similarly, if you only care about transferring value, you don't have to put anything in the data field. So you have the optionality to do both, but you don't have to. It's really up to whatever is kind of most useful for you. So then in terms of sending a message, right? The sender invokes CCIP send on the router. The router is the single entry point for all destination chains, so that's the only address here that the sender needs to know about. The router will bill the sender's subscription to make sure that this is economically viable. And then the router routes the message based on the destination chain that's specified, as well as based on the tokens that are being sent. So in particular here, when the sender calls CCIP send and transfers the tokens to the router transfers them on to the appropriate token pool. The token pool is token specific, so for each token, there's a dedicated token pool contract. And that, again, goes back to what I mentioned earlier about being forward-looking in the architecture of the system. Because what it enables us to do is to, in the future, support different types of tokens, put different security controls in place just by having different types of token pools. The token pools can also enforce security features like rate limits, ensuring that at most a certain amount of value, say, I don't know, $1 million, can be transferred per hour. And this is an attractive security feature Because if we think back about a lot of the hacks that have happened, right, there were vast amounts of money drained in like seconds. So if there had been rate limits in place in such cases, then an attacker could have stolen, at most up to the rate limits maximum, and that would have been it. In many cases, probably dramatically limited the amount of damage that would have been done. Right, so now we have the tokens in the token pool if the developer chose to send tokens. And then the router will forward the message to the appropriate on-ramp contract. Again, there's a correspondence between on-ramp contracts and destination chains. So for each destination chain, we have one on-ramp. And again, this is forward-looking because it enables us to do certain types of validation. For example, whether an address is in the correct format. For Ethereum, hey, is this 20 bytes long? In the on-ramp, but if new chains emerge, then we can have new on-ramps that can perform the appropriate validation for these chains. And then finally, assuming that the validation passes, the on-ramp will emit an event with a message and some metadata. Okay, so now this is where, for the first time, we're moving things between chains. So at this point, the committing DON, which comprises many oracles running OCR2, and which watches the on-ramp for any event submitted by it, will pick up the event. It will wait for finality of the events, right? We need to make sure that no double spends are possible. So it will wait, depending on how the source chain operates, maybe for a couple of blocks, maybe for a long time, until we are certain that whatever was emitted by the on-ramp is final. And at that point, the committing DON will then send a cryptographic commitment to the message that was emitted by the on-ramp, or maybe multiple messages to the commit store contract running on the destination chain. And that commitment will be signed by a quorum of the oracles in the committing DON. So now we, for the first time, moved things between chains. And so now I want to briefly explain to you what kind of commitment we use here, and then later on you'll see why that's attractive. So we're using a Merkle tree here, right? This is a very well-known construction in cryptography. This commitment is nice because it's constant size, regardless of how many messages we have. So at the bottom here, we have 4 messages. This commitment will be 32 bytes. If at the bottom we had 1 million messages, then the commitment, which, by the way, sorry, is the thing at the top of the tree, so the so-called root, would still only be 32 bytes. And that means that the committing DON always only kind of sends a signed 32-byte value, basically, to the other chain with a little bit of metadata. Another appealing property of these cryptographic commitments is not just that the commitment itself is constant size, regardless of how many things are in it. It's also that proofs, cryptographic proofs, that some message is indeed included in this cryptographic commitment are compact. So they're only logarithmic in the size of the number of messages. So even if I had 1 million messages, then still my proof here would only have like 20 elements. And yeah, finally, the commitment is binding, I should say. So if you change anything about the message, any message at all, you'll get a different commitment. Perfect. So this takes us to the anti-fraud network. So now we have a commitment stored in the commit store, and this is where the AFN will kick in. So the AFN is a completely separate system. It has a minimal trusted computing base. It's developed in a different programming language. It's developed as independently as possible from the primary system to ensure that any issues that might affect the primary system will, with high probability, not affect the AFN or vice versa. So the AFN here will monitor the on-ramp and the commit store. It will wait for a commitment to be stored in the commit store. It will then independently reconstruct that cryptographic commitment, that Merkle root, from the events that were emitted by the on-ramp. And then only if the reconstructed commitment matches will the AFN send a transaction to the AFN contract blessing that commitment. And later on, when we want to execute a message, the off-ramp will make sure that anything it can execute against will have been stored in the commit store as well as blessed in the AFN contract. So even if the committing DON here were to put some bad Merkle root in the commit store, still that would not be executable. Nothing bad would happen as a consequence of it because the AFN would not bless such a bad commitment. An interesting consequence of this is that CCIP is auditable because the AFN only uses on-chain information. The AFN does not talk to the committing DON. The AFN does not talk to the executing DON. The AFN only looks at information that's on-chain. which is public, and consequently, actually, anyone will be able to run an AFN instance themselves in audit mode to make sure that everything is working correctly here. DFN also has a second capability, which is to monitor for anomalies. And so what DFN does is basically it watches all of the contracts in the system continuously, and if it detects anything that goes wrong, so for example, execution of an unexpected message, unexpected changes in token balances, some kind of fork or reorg that's deeper than the finality depth on the source chain, the AFN will immediately trigger an emergency pause of the system. So again, if we think about some of the hacks that happened earlier this year, in some of the cases, these hacks went on for quite some time, many minutes. A first hacker attacked, stole some funds, and then other copycat attackers kind of jumped on the bandwagon and performed the same attack to extract more value. If an AFN had been in place in such a case, after the first fraudulent transaction would have occurred, everything would have been paused and shut down, and at that point, no further theft would have been possible. So this is, again, I think, a major security feature that we offer. And one thing I should mention here, there's also an AFN contract on the source chain. I just didn't put one there because otherwise it was going to get a little crowded here. But what all these contracts will do both on the destination chain and then analogously on the source chain is whenever they perform any action, they will check with the AFN contract whether the system is live or emergency paused. So if any kind of emergency pause happens, then all contracts from that point forward will be in a kind of pause state and will refuse to take any action until that pause is lifted. Cool. So now we have our cryptographic commitment in the commit store. We have a blessing in the AFN contract because the cryptographic commitment was indeed valid. So now we get to the part where we can execute the message and actually make things happen in the receiver contract on the destination chain. So again, we have an executing DON here that's comprised of many oracles running OCR2. And the executing DON will wait for a message to be committed in the commit store and blessed in the AFN contract, and then it will send an execution transaction to the off-ramp. And that execution transaction will include, as I mentioned, one of these succinct proofs that indeed the message is included in the commitment that's stored in the commit store. So now you may wonder, hey, why are we separating execution and committing, right? It could just be one step where there's one DON that bridges the information across. And there's a few reasons for that. So I already talked a bunch about the security benefits of doing this, but there's other benefits as well. So we get greater efficiency because we can batch many messages into a single commitment. As I mentioned, right, even if you have 1 million messages, the commitment will still only be 32 bytes large. Also that means that when the AFN does a blessing, right, it can bless many messages at once by blessing a single commitment. So this is more efficient. It means that we can run, at the same cost, larger DONs, which increases security. And it's also forward-looking because it means that we have a kind of transport layer that can deliver information between chains with a very high degree of integrity. And then we can put different types of message types on top of that. So right now, we're only looking at this programmable bridge. But if the ecosystem keeps evolving, we can layer other things on top of the transport layer that can provide new functionality as well, and they can share that security-critical infrastructure. All right, so as you remember, we were at the off-ramp now, right? So our executing DON sent the proof to the off-ramp. The off-ramp will validate that the proof indeed checks out against the commitment stored in the commit store. This is a cryptographic procedure. And it will also then check as part of this process when the commit store asks the AFN contract whether the commitment is actually blessed. And if the commitment for some reason isn't blessed, the commit store will refuse to validate the proof. And therefore, even if the executing DON, for example, were to try to somehow collude with the committing DON, to have bad information stored in the commit store, it couldn't execute it because the AFN would not have blessed it. Also, again, symmetrically with the on-ramp, where we have one on-ramp per destination chain, We also have one off-ramp per source chain. And again, this goes to this forward-looking design where we can have, for different chain types, different off-ramps that can provide different functionality depending on what the source chain requires. Cool, so now we're at the final step here of this message flow, the CCIP receive call. So again, symmetrically to how the router on the source chain acts as the single entry point for a developer that wants to send a message, the router on the destination chain acts as a single exit point for any source chain. So the router will invoke CCIP receive on the receiver contract. I will show you the signature of that function in a second. And the router will also bill the subscription of the receiver contract for the cost of executing the message. And then finally, I think another aspect that's important to mention is that messages are sequenced per receiver here. So if, for example, I have a contract A on the source chain sending messages 1, 2, 3 to a contract B on the destination chain, then these messages will indeed be delivered in order 1, 2, 3, and not in order 3, 1, 2, or 3, 2, 1. And this is, I think, nice for the developer experience because it means that developers don't have to worry about messages arriving out of order and gracefully handling that. So as promised, here is the API for the CCIP receive call. So this is an interface which then any contract that wants to receive messages via CCIP can implement. And so here we have a function CCIP receive that just gets a message structure. And that message structure is kind of what you would imagine, right? So you get the ID of the source chain that the message came from. You get the address of the sender of the message. Again, bytes, because we want to be agnostic to all sorts of chains and all sorts of address formats. Some arbitrary data, and the tokens and their respective amounts. And yeah, again, the only two parts that a developer has to worry about are CCIP send and CCIP receive. All the other stuff that I just showed, I think is neat, but is abstracted away from the developer. So ta-da, we're done, right? The message now made its way across the chain. But what if something went wrong, right? There could be various edge cases here. And of course, we're also carefully thinking about these. So to provide you with some examples, how do we gracefully recover from errors in case CCIP receive fails? So one possible failure mode here could be that the subscription is underfunded, right? There aren't enough subscription funds on the router, and then the DON will, of course, not execute the message because it wouldn't be paid. However, once enough funds are made available in the subscription, the DON will automatically detect that because it will retry periodically and will then execute the message. So if for some reason that ran out of funds, just need to top up and service will resume. Similarly, if the message reverts, right, maybe there's some issue with the receiver contract that caused the message to revert even though that wasn't really intended, then the developer has a choice what semantics they prefer. Maybe they want to ignore the reverted message and just keep moving on. Or maybe for them it's really important that they never miss a message. And in that case, they can enforce that a single reverted message will block the rest of the message sequence, and they can manually retry executing that message in order to be able to get the system unstuck, again, depending on what makes sense for their dApp. Cool, so now it's time for a demo. And I put a ping-pong emoji here because the demo consists of two contracts playing ping-pong. So we have a contract on one chain, Rinkeby, and a contract on another chain, Gurley, and they're going to pass messages back and forth. Unfortunately, so I was planning to do a live demo here with my laptop. Unfortunately, there's some issue with the AV setup, so the live demo isn't going to work out. So instead, you're going to get the slightly lamer pre-recorded version. But believe me, the live demo works. I tried it out this morning. Can we move to the next slide? Can we move to the next slide, please? There we go. So I'm just going to briefly show you the code of this example ping-pong contract. It's just a relatively short Solidity contract. And so first of all, here we have the CCIP router interface, right, which is the interface that the CCIP router contract implements. This is the single entry point here. And that just has a CCIP send function that you can send a message on. So this is what we had already seen, nothing new here. Next slide, please. And then analogously, here is the CCIP receiver interface, which we've also already seen. Again, just the CCIP receive function here and the received message structure. And this is the interface that a contract that wants to receive messages using CCIP would have to implement. Next slide, please. So just to go back to this, this is the receive interface will be implemented by the receiver contract, and the CCIP router interface is implemented by the router, and all the other stuff is abstracted away, and we don't have to worry about. Next slide, please. So this is where we get into the meat of the actual contract. So our demo contract here inherits, first of all, from some owner contract. So there's some owner, nothing special here. And it also inherits the CCIP receiver interface, which enables it to receive messages. It has two events, a ping event and a pong event, unsurprisingly for a ping-pong contract. We configure the router on which it receives messages and the router on which it sends messages, the chain ID of its counterpart on the other chain, the address of its counterpart on the other chain. Then we have a constructor, and we have a set counterpart function, which are just for configuration. Next slide, please. And so this is where we actually get into the kind of interesting code that's not just plumbing. So now we're at line 53 or so. And here we need a way to start the ping pong, right? So the contract will always respond if it gets a message, but something needs to kick off that chain reaction. And so the way we do this here is that we say the owner can kick it off by calling start ping pong. And that, in turn, will just call this internal respond function, which will set an initial count. And then as we ping pong back and forth, we will keep incrementing that count. So if the ping pong count is odd, then we have a ping. And if it's even, then we have a pong. So ping, pong, makes sense, right? And then we now need to send the message. And so can we go back? Thank you. So we take our ping pong count. We ABI encode it because we need some representation that's just bytes. And then we stuff it in our message, which we're sending here. So we also put the address of the counterpart on the other chain, the encoded data, which is just the count. And because here we don't really care about sending tokens, we just leave the tokens empty, right? So we give a 0 length list for the tokens and a 0 length list for the amounts. And we just get the messaging functionality. And we set the gas limit to 200,000 because why not? And then we, on the sending router, call CCIP send with this message we just prepared. Next slide, please. Perfect. And now CCIP will do its thing, the whole flow that I just explained. And on the other side, on the counterpart, which runs the exact same logic, the CCIP receive function will be invoked by CCIP with the message. And important to note here, we have this modifier only router here, which is important for security because we need to enforce that only the router called CCIP receive, not just some arbitrary contract. We also do 2 more security checks, access control checks, so we make sure that the message indeed comes from the source chain that the counterpart runs on, and we make sure that the address of the sender is indeed the address of the counterpart and not just some arbitrary other contract. Then we decode our message into the count. We increment the count by 1, and we call respond, which I had already shown you. Can we go back 1 slide? Right, so that was just the same logic here, where we emit our event and we send a message back. And that's it. So between line 53 and next slide, please. Next slide. Yeah, between line 53 and line 81, that's all the logic we need. So roughly 50 lines of code or so. And then we have some plumbing code, which in the live demo I would have briefly showed, but here I don't have on the slides. So now let's move on to the not live demo, please, which is a small video showing this in action, which I recorded this morning on Rinkeby and Gurley. So here we have Etherscan. We have Etherscan for Gurley on the left, and then in the other tab we have it for Rinkeby. So yeah, Gurley, Rinkeby. Let's zoom in a little so you guys can actually read what's here. And so I've already started the ping pong at this point, just for context. And so you can see these internal transactions happening here, right? So Those are just the ping-pong contract being called by the CCIP execution. So if we look at the contract here, we have the ping-pong demo contract running on both chains. Source code is verified below. And now we can see the events. And so scroll to the bottom. So here we have the ping events happening on Gurley, and then we have the Pong events happening on Rinkeby. And so here we have the first ping, which has the number 1 here. And then on Rinkeby, we have the corresponding Pong with the number 2. And then that goes back, and we get another ping with the number 3, and another Pong with the number 4, and so on and so forth. And I think here we have something like, I don't know, 10 ping pongs total or something that we show. All right, so that was ping number 9, and then correspondingly here we have ping number 10, 0x0a in hexadecimal. Yeah, so there you can just see the calls and kind of method IDs. And that was the recording. So this is the system working live in action this morning, sending messages back and forth between 2 EVM chains. And the neat thing is, right, you kick it off once, and then it just keeps going kind of forever, and CCIP handles the rest until at some point you maybe run out of funds. So yeah, hopefully that demo showed that with just a tiny bit of code, you can leverage all of this. And as a developer, you don't have to worry about all the details. But hopefully, I could also give you a glimpse under the hood and provide you with an understanding for how CCIP is built from the ground up for security, from the ground up built for interoperability, and is forward-looking to be able to integrate new chains and new ecosystems in the future. And of course, also is is built for, well, whatever the third one was. This brings me to the end. So we're alpha testing synth teleporters with synthetics as a use case. We're also doing a proof of concept with Swift that I think Sergey mentioned yesterday. So we're helping the Swift network become interoperable across all blockchains. And if you're interested, then please reach out. There's a QR code here. There's a link here. We'd love to talk to you and would love to understand how we can fulfill your needs in building native cross-chain dApps. And yeah, thanks a lot for your attention.